G'day folks, and welcome to another tutorial. So today we're going to start looking at the final instructions in the MMX instruction set, and I've chosen to do the Boolean operations and the comparison operations at the same time because I think that in MMX they sort of go hand in hand, as we'll see. Okay, so this is comparisons and Boolean operations I'm going to break into two tutorials because I think that it's pretty confusing and pretty long. Anyway, the MMX Boolean operations. There's four of these. We've got packed and, packed or, packed exclusive or, and packed and not. So this third one here will probably be new, but the others you probably recognize from regular x86 assembly. They all take two parameters as per usual with MMX. We've got an MMX register as the first parameter, and the second can be MMX register or 64-bit memory operand. And they all do exactly the same operation as their x86 counterparts, of course excepting the and n here. Alrighty, so there's no data sizes for the Boolean operations in MMX. It doesn't matter if you're doing a packed and on words or bytes or D words, they're all going to produce exactly the same results. So yeah, no data size. Here's the truth tables for the first three. We've got what's that, P and up here, which sets the result bit to 1 only if both of the operands have a 1 in that bit. We've got packed or, which sets the result bit to 1 if either of the two operands, A or B, are 1s, or indeed if both of them are 1. And then of course exclusive or, which sets the result to 1 if one or the other has a 1 in it, but not if both have a 1 in the particular bit. Okay, so that's pretty cool. Packed and not. Okay, so here's a new Boolean operation. This is not really one of the Boolean operations, but it's been added to MMX, I believe, because of the comparison instructions. They make things a lot easier. Anyway, it's pretty much the same as flipping all of the bits in op1 to their opposites, so 1s become 0s and 0s become 1s. That's for all 64 bits in op1, and then ANDing the two together. Okay, so this is the truth table just here. I've got op1 over here, A, this is the bits in A, this is the bits in B, and here, not A, that exclamation mark is supposed to mean not. I've flipped the bits of A, so all of the 0s become 1s, and all of the 1s become 0s. And finally, this is the actual answer over here of packed and not. So I've just ANDed not A with B, and we end up with a 1, just there. So the only time that packed and n gives you a 1 is if operand 1 had a 0 in that bit and operand B had a 1 in that bit. Then it gives you a 1 for the answer. Otherwise it gives you 0s. A couple of things to note. First of all, it's op1 that's complemented, not op2. So A in this example, in the truth table, is complemented, not op2, and the answers would be different. If you draw out a truth table for what happens with complementing B instead, you'll see that the answers in the end are different. Also, weirdly enough, it's not, as the mnemonic suggests, and the two together then complement the answer. That gives you a different answer as well, so just be careful. Alrighty, so it's not the first operand, and then and the two together. And yeah, this instruction mostly helps with the comparison instructions, as we'll see next shoot. Yeah, little joke. Alrighty, comparisons in SimD. Okay, this is where stuff sort of starts to get a bit confusing. But comparing in SimD can't be the same as regular x86. There's only one flags register in x86, so you know that single flags register can't be used for multiple comparisons that we do in SimD. So instead of using a flags register, MMX sets the first operand. Each element of op1 that passes the test is set to all 1s in binary, and those that don't pass the test is set to all 0s in binary. Okay, we'll go into greater detail in a minute. But there's 6 instructions. We've got packed, comparison, for equality of bytes, packed comparison for equality of words, packed comparison for equality of D words, packed comparison for greater than of bytes, packed comparison for greater than of words, and packed comparison for greater than of D words. So there's actually only two comparisons that we can do in MMX. We can do equality, we can check for elements that are equal, and we can check for elements that are greater than. Each of these instructions takes two operands, MMX register, and the other is an MMX register or mem64. And something to be very careful of is that all greater than comparisons are signed. Alrighty, so that's pretty much all it comes down to. We've got we can check for equality, we can check for greater than, and we can check bytes, words, or D words. What do they do? Alrighty, so the elements in op1 are compared to the corresponding elements in op2, and if the elements pass the test, all of the bits, get rid of that little thing, all of the bits are set to 1, otherwise they're set to 0. So the CPU, essentially what happens is it creates a mask of 1s for each element that passes the test, be the test greater than or equal to. That should be equal to, not less than. Okay, so they create a mask. 1s represent the elements where the test was true, and 0s represent the elements where the test failed. And setting all bits to 1 in a register is the same as setting it to -1. It's also the same as setting it to FFH if we're using bytes, 4 Fs in hexadecimal if we're using words, or 8 Fs in hexadecimal if we're using D words. The register itself becomes the flag. It's a little strange, but we'll see how it works. And then you can use that mask of 1s or 0s, or these Fs. You can use that to do pretty much whatever you want. Let's have a look. So an example of, here we've got packed comparison for equality of bytes, and yeah, that's pretty much what it'll do in summary. This will set all bytes which are shared in MMO and MM1 to FF in hex, and the rest will be set to 0. Let's have a look. Okay, so yep, this will be the answer in MMO down here. So first of all, I've drawn it out here, sort of how I like to think of it. So -6 equals 4 is going to be the first thing that the CPU will try and figure out, and then it'll put either FF down here or 0, 0. And then it'll check the next one. Does 0 equal 0? And if it does, it'll put FF down here. If it doesn't, then it'll put 0 in that byte. Of course, 9 equals 9, and 3 equals 2, 8 equals 7. It'll always just put 0, 0 down here, or FF in hexadecimal. Let's have a look. Okay, so in this particular example, there was 3 bytes in MMO that were also exactly the same in I think we used MM1. So the 0 and the 0 were equal, so that's become FF in the corresponding byte in MMO. And the rest, like the -6 here, does not equal 4, obviously, so that becomes a 0. Does that make sense? Over here we've got FF because 5 and 5 were shared in both MMO and MM1. Alrighty, so that's pretty much all that happens. Just the corresponding bytes are compared between the two parameters, and the answer gets either FF or 0, 0. Alrighty, so here we go, greater than. Another example. Here we're using words. Once again, I've got MMO and MM1, and we're checking for greater than here. So yeah, that pretty much sums it up. We're going to get word-sized answers here, so 4 Fs in hexadecimal or 4 zeros in hexadecimal. Anyway, I think I've stepped through this one. Let's have a look. Yep, here we go. So the first thing that the CPU will ask, or it'll do it all in SIMD all at the same time, but if we step through it one at a time and pretend, we can see that it says, is -6 greater than 4? It's obviously not, so the answer in MMO will be 0, 0, 0, 0. The next one it goes, is 8 greater than 9? Once again, the answer is no, so the answer in MMO is 4 zeros. Is 8 greater than 7? Well, the answer is yes. So the answer in MMO is 4 Fs in hexadecimal, or -1. And here we go. Is 10 greater than 5? Once again, the answer is yes, so it gets -1 as well. So in this example here, the greater than example that we just used, we get -1 in the top 2 words of MMO, and the bottom 2 words will be set to 0. Okay, here's something to be careful of. The packed compare greater than that we just looked at is always signed. Alrighty, so yeah, I've written out some code here just to illustrate a problem that might come up. Yeah, one other thing that I want to point out is you don't need the square brackets around the A here. Just here we're moving a quad word into MMO from the array A that I've defined up here in the data segment, and yeah, there's no need for square brackets. Anyway, this is the line here that we're really concerned about, P greater than B. So pretty much just move A into MMO, B into MM1, and then do the comparison. But let's see what we get. Okay, so this is just highlighting that one line. Okay, everything's working pretty well. We've got 8 comparisons to do since we're using packed compare greater than bytes. And the first thing that it asks is -6 greater than 4. The answer is no. Is 0 greater than 0? The answer is no. Is 9 greater than 9? The answer is no. Is 3 greater than 2? Well, yes it is. So it gets FF in hex. Is 8 greater than 7? Yes it is. Is 152 greater than 6? No. What's happened here? Okay, so the other ones that it gets right is 5 greater than 5, no. Is 1 greater than 9, no. But it has got one wrong here. Is 152 greater than 6? And MMX will tell us that no, it's not. Why? Well, that's because 152 in binary is 100, 11, 000. And MMX comparisons, or MMX greater than comparisons, are always signed. So the CPU doesn't see 152 as 152. It sees it as the signed value -104. What it's really asking here is -154 greater than 6? The answer is of course no, so it puts 00 there. Alrighty, so just be careful. Remember that greater than for bytes, words and D words is always signed in MMX. Alrighty, so to finish up, I just wanted to go through a few tricks. These are going to come in handy next shoot, particularly these first two I think. But we've got setting a register to all zeros, setting an MMX register to all zeros, that is. We know how to set a x86 register to all zeros. Setting an MMX register to all ones as well is useful. And finally, this is a pretty big example, but simple branching in SIMD. Okay, so first of all, setting a register to all zeros is exactly the same as setting a regular x86 register to all zeros. And all you pretty much got to do is exclusive OR the register with itself. So packed XOR MMO MMO will set MMO to all zeros. We can also use the AND N instruction, that weird new Boolean instruction, and packed ANDN MMO MMO will set it to 0 as well. Pretty good. Okay, setting a register to all ones is pretty easy as well. All you have to do is use packed compare for equality and the same register. So here we're setting MMO to all ones. Obviously each of the bytes in MMO is going to be equal to each of the bytes in MMO since it's the same register. So that just sets every byte in MMO to FF. And you don't have to use pcomp equal B. You could use or you could test for equality with words or D words, it doesn't matter. It's going to do exactly the same thing. So yeah, pcomp equal and anything, if you use the same register as both operands, we'll set it to all ones. Here we go. So simple branching. This is the final example of the day. There's a bit of a problem with branching in SIMD, and that's that it sort of goes against the very essence of SIMD. SIMD is about performing the same operation to all elements at once, and the essence of branching is exactly the opposite. It's that each element could potentially take a different path. So branching in SIMD is pretty interesting. Well, we've got to think pretty hard about how to achieve some of these things. Anyway, I've got a little example here. So I've got two arrays, one called A and one called B, and we're just saying that they've got 4 words in each for this simple little example. And all I want to do is achieve exactly this, the C++ code. If AX, the X just means a particular element. If a particular element in A is equal to a particular element in B, then I want to set that element in A to 10. Otherwise, I want to set that element in A to 0. So a little branch here. There's 2 possible options. And achieving this in SIMD is, I don't know, it's not terribly hard, but it's more difficult than just writing out the C code anyway. Let's have a look. Okay, here's my code just here. I've got my code just here, and down here I've got some just notes about what each line does as we step through. That note shouldn't have appeared yet, but anyway. Okay, so over here I've got my 2 arrays at the top, A and B, 4 words each. So this is word 0 over the right, word 3 over the left, and here I've got RAX, which currently has garbage in it. I don't know or care what's in there at the moment. And the same with MMO and MM7. I've drawn MMO and MM7 up as words, since that's what I'm going to be using them as. And yeah, they're filled with garbage at the moment. Okay, so the first line, mov RAX 10, we know what that's going to do. That's just going to stick a 10 in RAX. And the second line, move double word into MM7 from EAX. And all that does is pops a 10 down in the bottom of MM7. And it also clears the top of MM7. Do remember that. Alrighty, so the second line, this first 4 lines here, all we're really doing is broadcasting 10 to all 4 words of MM7. Okay, so there we've got 4 10s in MM7. That's exactly what we want. And the next line, mov q MMO q word pointer A, that just moves the array A into MMO, because we can't use memory operands for both of the MMX instructions below. So yeah, we've got to move one of them. We've got to move one of these arrays into an MMX register. Okay, the next line, packed compare for equality words. This was pretty much the first line of the C++ code that we had on the previous slide. This is where we actually perform the comparison. So we test if each of these words in the array A is equal to each of the corresponding words in the array B. And the answer goes into MMO. So what we can see has happened is that -6 equals -6. Why, yes it does. So it gets FFFF. Does 13 equal 9? No, so it gets 4 zeros. Does 8 equal 8? Yes, so it gets 4 Fs. And finally, does 42 equal 5? Well, no it doesn't, so it gets 4 zeros. Fair enough. We've actually got masks here. We've got masks of 1s or 0s, which means that in the very next line, when we AND that mask with the 10s in MM7, we actually end up with the answer that we're looking for in MMO. We get 2 10s in the places where the words were the same in the 2 arrays, and we get 2 zeros where they were different. So the -6 and -6 gives us a 10, 13 and 9 gives us a 0, etc., etc. And the final thing that we do is move that answer that we got there back into the array. There we go. Move quad word q word pointer A from MMO. And we end up exactly with what we were after. We've pretty much said any words that are the same in the 2 arrays become 10, and any words that aren't the same become 0. Good? Alrighty, so that's the end of the first part of the tutorial, where we're looking at the Boolean operations and comparison instructions. And I'm going to break right here, but you might have noticed that we were missing a bunch of comparison operations. Say less than or equal to, greater than or equal to, and not equal to. And MMX doesn't actually provide instructions for that. It only provides the equal to or greater than operation. So next shoot we're going to have a look at how you achieve these in MMX, and yeah, that's pretty good. So we've actually looked at every instruction in the MMX instruction set. Anyway, thank you for listening. See ya.